The other one is monotonic and in a slowly increasing way. We want to come up with something that if we do an and or and we tweak things just a little bit, we would like it to be continuous. In other words, we would not like to tweak whatever we're doing just a little bit and then boom, it changes from over here to over here. It needs to be a continuous sort of monotonic transition from one result to the other one. So let's look at ANDing and ORs, and there's a couple of ways to do it. As you know, in matrix multiplication, there's two ways to multiply vectors. One of the ways to multiply vectors is to take the inner product, in which case you get a scalar. The other one is to take a outer product, in which case you get a matrix. So there's the inner product and the outer product, two different ways of multiplying vectors in regular linear algebra, if you will. So let's take a look at some different fuzzy membership functions. Here we have fuzzy membership functions, and we want to aggregate them in some fashion. By aggregate, I mean we either want to do an and or an or associated with whatever the result is. So on the left, we have the membership function for A, and A is the set of numbers which are near to an integer. And these are numbers which are close to an integer. And I've chosen the mu sub A here on the left as being the fuzzy membership function of numbers which are close to integers. And you can see if we're right on an integer, the membership function is 1. There's no doubt about it. But as we stray from an integer and get further from an integer, the membership in the set of signals which are near to an integer, it begins to decrease. And we actually have a periodic function that you can see here. So we talked about probability versus fuzzy logic. And I think you can see here that the left-hand plot could never be considered anything to do with probability. It's not a cumulative distribution function. It's not a probability density function. It doesn't have an area of 1, for example. So this sort of thing doesn't occur in probability. So we do have at least this difference. This is not the only difference, of course, but I think that that's one thing that distinguishes fuzzy from probability, if you're still wrestling with that concept. We have something here which goes on forever and ever and ever, and it's a periodic function, and that's kind of interesting. So on the right-hand side, we have the set B. This is a fuzzy set. This is x is close to 2. And we've talked about this also, and don't forget, if you generate a fuzzy membership function, it's probably going to be different than the fuzzy membership function that I generate. There's a number of different membership functions we could assign to the fuzzy sets A and B. Notice in both cases there is a fuzzy linguistic variable. The first one is x is near. Near is a fuzzy linguistic variable. And it's something that we can measure. It's ordinal, but we can measure it. But we also, in human conversation, talk about things which are near to one another. So here we go. We've been talking about fuzzy logic, fuzzy sets, generated by Zada in 1965. Now with applications all over the place. As I mentioned previously, fuzzy sets got their genesis and applications in Japan. In fact, decades after Zada's original paper. It turns out there were two guys, Sagino and I think it's Takaki, who pioneered the idea of use of of fuzzy logic in a number of different applications. We talked about last time fuzzy versus crisp probability. And then we're starting to get into the actual logic of things. If you're familiar with Boolean logic, then you know there's such operations as and, or, complement, and it must meet fuzzy, crisp boundary conditions. In other words, whatever we come up with for fuzzy sets better work also for crisp sets, because we've seen that crisp membership functions, which are always 0 or 1, you're either totally in the set or you're totally external to the set, that they are a special case of a fuzzy membership function. And so therefore, if we come up with something, and we're all familiar with what happens in Boolean logic, it better meet the special case of Boolean logic. It should be commutative. A and B should be the same as B and A. A or B should be the same as B or A. So that's commutative. It should be associative. Um, the other one is X is close to 2. That's the set B. X is close to 2. The fuzzy linguistic variable here is close. We all have an idea of what close is, but again, it's a fuzzy sort of concept. And these are the membership functions which I have generated. So it turns out that if we look at the different logic operations, how do we do, for example, the set of things which are near the set of numbers which are near to an integer and close to 2. So we're applying a logical sort of operation. Now, it turns out that the logical operation for combining these membership functions into a new set are numerous. I'm going to go over the way that Zada, in his original 1965 paper, talked about the way to perform operations such as and, ors, and complements. So here we go. It turns out that the fuzzy union is the maximum of the two membership functions. That is mu sub A and mu sub B. So you take the two membership functions. This is Zada's original idea, and you take the maximum of them. First, it meets the crisp boundary conditions, and I'll review this in a minute. If, for example, mu sub A and mu sub B are crisp membership functions, it turns out that it degrades to, or I shouldn't say degrades, but it becomes the conventional Boolean OR operation in terms of a fuzzy membership function. And it turns out that if both mu sub A and mu sub B are crisp membership functions, they're between 0 and 1. And if you take the minimum or maximum everywhere, you also get a membership function which is between 0 and 1. And it does turn out that it meets the boundary conditions for an original crisp set. It is commutative. The maximum of A and B is the same as the maximum of B and A, so it checks that. It is associative in the sense that if you take the max of A, B, and C, it doesn't matter which order you take them in. Remember what associative is? Associative is it doesn't matter the order that you're taking it in, like addition is associative. If you do A plus B plus C, it doesn't matter if you add A plus B first or A plus C first. As long as you get them all in, it doesn't matter the order that the addition is performed. And so this, again, is associative. It's idempotent. And it's idempotent in the sense that if you do a maximum of 3 and 3, you get 3, right? And this is idempotent. So if you take the maximum of two identical membership functions, you get exactly the same membership function back. Idempotent means if you do it twice, it's the same as doing it one time. It's the same as doing it 6 times. It's kind of like sweeping the floor. If you sweep the floor once in a room and you go back immediately and you sweep it again, well, you haven't changed anything. So that's what idempotent means. It's a really nice, fun way of doing things. Monotonic, the maximum is a nice smooth function, so things don't operate really, really quickly. They don't change very, very quickly. You can't have a drastic transition from the OR operation going from one to the other. This, by the way, is the logical OR, and it's referred to as disjunctive. It's a disjunctive operation. And let's give an example for the two sets that we looked at previously. If we looked at the two sets that we looked at previously, that A or B, we get that A or B, and I'm using the plus there as the logical Boolean and, X is near an integer or X is close to 2. So the new membership function, which is mu of A or B, is shown here on the bottom. It is the maximum of the two functions. So you can see that as we do this, that we're going to get the solid black line if I take the maximum of the two different functions. So this is the membership function for the maximum of A and B, or the black is the membership function of the OR operation of X is near an integer or X is close to 2. So if it's near to 2, it's got a big membership. If it's near to an integer, it has a big membership, and this conserves the idea of the OR operation. So this is very kind of cool, and it turns out it does meet the boundary conditions for crisp sets also. So, as you might expect, if we do the maximum for the union or the OR operation, then for the intersection, we probably do the minimum. And this is what Zada did in his original 1965 paper, and it works very, very well. It does meet the crisp boundary conditions. In other words, if mu sub A and mu sub B are both crisp sets and only have a value of 0 and 1 as a function of their arguments, then if we take the minimum of these two functions, the minimum of the two functions will be 1 if both of the membership functions are 1, and it'll be 0 all the other cases. If one or both of the other membership functions are 0, it becomes 0. So it does meet the crisp boundary conditions. It is commutative. It is commutative in the sense that if we take the minimum of A and B, it's the same as taking the minimum of B and A. It is associative. If you have three numbers and you take the minimum, it doesn't matter which order that you take the minimum in. It is idempotent in the sense that if you do the minimum of mu sub A and mu sub A, we do the minimum of both of those, then we get the same exact result. So if you do the AND operation, then it turns out if you do the AND operation between a set and itself, you get back the same membership function. That's kind of cool. It is monotonic in the sense that the minimum is a smooth function, and if you change it a little bit, then you don't change the minimum a lot. So we want to have that smooth sort of function. So then let's look at the case of A and B. A and B is denoted by the dot there, and it's equal to the set of x such that x is near an integer and x is close to 2. It has to meet both of those criteria. It has to be near an integer and it has to be close to 2. And so this is given by the minimum operation. You can see here that we have the two original membership functions denoted by the dashed lines. And if we take the minimum, we get the membership function in the solid lines. And as you can see, does this make sense? Does this make sense as a membership function of x is near an integer and x is close to 2? Yeah, it does. It does make sense in a linguistic sort of way. So these were the things which were proposed by Zada in his original 1965 paper. Now, it does turn out that, as you've seen, fuzzy logic is very robust in terms of choices. You could choose a totally different membership function here and get something kind of interesting. Your membership function can be totally different than mine. And it does turn out that also this idea of and ors can be totally different. In some places, it's treated as follows. The OR operation is treated as the summation of the two membership functions as opposed to the maximum. And this is used quite a bit. In some places, A and B is used as the multiplication. And we'll talk more about that later, but I just want to emphasize now that Zada's original idea of min and max works very, very well, and it has a lot of optimal properties. However, it's not the only way that you can do an AND and an OR in a fuzzy logic sort of sense. There's different ways to do it. Another thing that we have is between AND and ORs, we have complements. And what is fuzzy logic in terms of complements? Well, that's given by the next line. The membership function of A, and you'll notice that the A has a bar over it, and that bar over the A means it's the complement, is simply equal to 1 minus the membership function. Now, so the complement of A is x is not near an integer, and that's equal to 1 minus the membership function of A. Now, the membership function for A is given by a dashed line here. So the fuzzy set of numbers which are not near an integer is given by the solid line. That's equal to 1 minus the dashed line. And so this is the idea of a complement. It does indeed happen for crisp sets. If you think about it, a 0 not in the set becomes in the set if you take a complement, and things in the set become out of the set when you take the complement. So a 0 becomes a 1, and a 1 becomes a 0. And that's kind of what we see. I want you to look at this and see if it is consistent with your intuition about a fuzzy membership function of things which are not near an integer. And it does make sense. This is a fuzzy membership of things not near an integer. So this is kind of wonderful because as we go along, we would like to take this idea, a fuzzy membership function, and every time we see it, make sure that it is consistent with our intuition as to what the fuzzy linguistic variable means. And I think you can see that this is consistent. That black membership function is the set of numbers which are not near to an integer. The other thing that it has is that it does have a distributive property. It does that A and B does have a distributive property. You're all familiar with the idea that A intersect B plus C, as you see in the light blue box, is equivalent to the subscript shown on the right. It's A plus B. It's A or B and A plus C. So in other words, the A is distributed among the B and the C. So that's kind of interesting. That also works for a fuzzy membership function. So if we do, for example, the minimum of A, and what is B or C? Well, B is the maximum of B or C, right? It's the maximum membership function. So the minimum of A and the max of B and C is equal to the thing that we have on the right. Let's see, the A or B is equal to the max of A or B, A or B, and the A or C is equal to the max of A and C. So we want to take those two numbers and we want to perform the minimization of it. So you see what I've done here is I've simply taken the definition of ands and ors and I've applied it specifically to these um, sets here. So A and paren B or C is the same thing as paren A or B and paren A or C. And if we interpret that again, we get the equation which is shown at the bottom of the screen. In the case of the and, we want to take the minimum between the two functions, but before we take the minimum, we have to do the or of B or C. So that minimum of, I'm sorry, that B or C is the maximum of B and C. Then we take whatever that is and we do the minimum of A and then that maximum. So that's the interpretation of the left-hand side in terms of minimum and maximum. If we look at the right, on the other hand, we need to first of all do A or B. That's the max of A and B. And that's going to give us a membership function. We also have to do the max of A and A C. And that's a membership function. Then we need to take those two membership functions and we need to do the minimum of it in order to do the intersection between these two sets. And it does turn out one can show that the minimum of A and that the minimum, well, that the equation at the bottom of the screen is indeed correct. And I'm going to give you a homework assignment, and it'll be on the spreadsheet to actually prove this. And the question is, how would you prove this? There's a couple of ways you could do it. Number one is that you could look at a formal proof where you actually go through minimum and maximum, or you could go through A, B, and C and look at the different ways that A, B, and C can be related. For example, A can be bigger than B, can be bigger than C, or you can have that inequality kind of shuffled around. A could be greater than C, which could be greater than B. So if you prove it for all of the different combinations of A, B, and C in terms of their relationship to one to another, I think that suffices for a proof. So you can look at it and again prove it one of two ways, one of which is to go through the mathematics of minimum and maximum, and the other one is you can do kind of an exhaustive proof by assuming some sort of ordering and making sure that you have all of the different orderings of A, B, and C. Now, that is associative. We do have the intersection is distributed over the union. Well, it turns out in that this looks very familiar because it looks like what we're familiar with, because if we have the dot being multiplication and the B and C being addition, then this is kind of obvious, right? Because that's true for multiplication and addition. But it turns out that also union is distributed over um, over intersection. And this is what we have on the next slide. It's distributed over intersection. A or B and C is the same thing as A and B or B, A, and C. So you've seen this. This is kind of a curious thing in Boolean logic because we're not used to having addition being distributed over multiplication. It isn't true. But if it's a Boolean operation, indeed, it is true. And just like before, we can go through the operations that are needed to perform the results here. So let's take the A or B and C, where the B and C are in parentheses. First thing we have to do is B or C, so we take the minimum of B or C, B and C, and then we have to take that new number and we have to perform a AND operation with A, which for fuzzy logic corresponds to a maximum. So we need to take the maximum of A and the minimum of B and C. Now, curiously, I'm claiming here without proof that this is exactly the same as what you see on the right-hand side, that mu of A and B or A and C is the same as what you see on the right. In other words, distributing the Boolean logic over the Boolean logic of anding or oring over the Boolean logic of uh, anding, if you will. And on the right, what do we have to do? We have to figure out the membership function for A and B. That's determined by doing the minimum of A and B. We also have to figure out the intersection of A and C. That's given by the minimum of A and C. Then we have to take those two new sets, and we have to take the maximum of those two numbers. And I'm claiming that this left-hand side is equivalent to the right-hand side, although it doesn't look like it on first. Well, I shouldn't say it doesn't look like it. It isn't apparent upon first inspection, right? So I'm going to ask you to prove this also, that indeed that fuzzy logic has union distributive over intersection. It applies De Morgan's law. If you remember in Boolean logic, there is something called De Morgan's law, which says that if you look at the subscripts of the fuzzy membership functions, that the complement of B and C is the same as the complement of B or the complement of C. So you've seen this in De Morgan's laws, and De Morgan's laws takes on two different forms. It takes on the complement of A and B, and then the complement of A or B. And we'll look at this second case in a minute. So for the first one, we have to first of all compute the membership function for B and C. Well, what is that? That's the minimum of B and C. Then we take the complement. The complement is equal to 1 minus this, 1 minus whatever that membership function is. So that's the interpretation of the left-hand side here. On the right-hand side, we have to take the complement of B and then the complement of C, and then we have to do an OR operation on it, which corresponds to a max. So this says that the maximum of 1 minus A and 1 minus B is the same as 1 minus the minimum of B and C. On first inspection of this, if you've never seen it before, you might think, well, that's interesting, but it's not obvious. And so I'll be asking you to prove this also, that De Morgan's law is satisfied. Here's the other form of De Morgan's law, which says that the complement of B or C is equal to the complement of B and the complement of C. So again, this is getting boring, but it's probably good to go through it. How do we get the complement of B and C? First of all, we take the ORing of B and C by taking a maximum, and then we do the complement by taking 1 minus that. Remember that the complement was equal to 1 minus that. And then we go over here and we take on the right-hand side, we take the complement of B and the complement of C. Well, guess what? I got my A's and B's goofed up here. This should be a B and this should be a C. So hopefully that's self-correcting. So it does turn out that if you do A for C, that the minimum of 1 minus C and 1 minus B is the same exact result as you see on the left. And again, you look at this and you say, well, I don't know if that's obvious. No, it isn't obvious, I think, on first viewing, but indeed it is a truth. And it does turn out that Zada's original insight into the conservation of these different Boolean logics and fuzzy logic was very I think it was very insightful how he could choose minimum and maximum to meet the boundary conditions of minimum and maximum, and then apply it to all of the different rules associated with conventional Boolean logic, and showing that indeed that it does work. Now, it does turn out that you cannot have all of the different Boolean logic applications duplicated in fuzzy logic. And there's a proof in Clear and Folger that you can't have all of these, and the one I'm going to show you next. So there's a big list of things you would like to see reducing to regular logic. And everything we've seen thus far reduces to regular Boolean logic. But it turns out that this isn't true for the law of excluded middle. The law of excluded middle says that if you take a set, now this is a Boolean set, and you AND it with its complement, you always get the null set, right? You always get the null set. Well, it doesn't apply for fuzzy logic. If you take a fuzzy membership function and you apply the law of excluded middle and you do the intersection of A with its complement, you do not get zero. And zero is the membership function of the null set. So if you have a null set, its membership function is zero. And likewise, the universal set for everything for all numbers is equal to one. So we have zero assigned to the set of the null set and one assigned to the membership function of, if you will, the universal set. So let's see what this means. And let me argue with you that this actually makes sense in terms of fuzzy logic. We'd like it to meet this boundary condition, but it really doesn't. The set of numbers close to 2 and the set of numbers not close to 2 is not equal to the null set. The set of numbers equal to 2 and the set of numbers equal to not close to 2 do not equal the null set. In fact, I think what I want to try to do now is I want to go to a little tablet here. So with this, let's do the following. You remember the set of numbers which are close to 2, and it looks like this. That's a fuzzy membership function for numbers which are close to 2. Is that okay? Now we have the other case of numbers which are not close to 2, which is 1 minus this. So what does this look like? Well, I think it looks something like this. Okay. So this is the first one is the membership function for numbers which are close to 2. The second one is the membership function of numbers which are not close to 2. So this is a complement. And if we OR these together, that means we take the maximum of these two numbers. So we want the membership function of A and not A, which is equal to the minimum of mu sub A and mu sub not A. So it's a minimum of these two functions. So what would that look like? Well, the minimum of these two functions would look something like this. Let me actually make it a little bit thicker. That's the minimum. And we can see with the minimum that we have something kind of cool. We would like, if you will, we would like A intersect A dot to be equal to the null set. And this is true for Boolean. But for fuzzy, A dot A not is not equal to the null set, which is fuzzy. because again, the membership function for the null set is 0 everywhere. And we see if we do the minimum of these two functions, we don't get this. So let's analyze this and see if it makes sense. We want numbers which are what? That's what we have. Numbers which are close to 2 and not close to 2. Is this thing in the dark green, does that capture that? Well, I don't know. Let's do something which might be a little bit more intuitive. Let's take the membership function of tall men. And so let's put here 6 foot, 7 foot. So I think the membership function for tall men would go something like this, right? I think if you're at 7 feet, then there's no doubt that you are in the set of tall men. 6 feet, you're kind of in the set, you're kind of not in the set. So what do we do if we look at the set of men that are not tall? Well, we would get something like this. And I think this example makes more intuitive sense than the numbers close to 2 and not close to 2. Let's see what we're going to do if we want to take the membership function of men who are tall with the membership function of men who are not tall. We would take the minimum, right? The minimum would look like this, wouldn't it? Okay, so what's interesting about this is as follows: is somebody that's, say, 5'11". Let's say that that's this point, 5.11. Is that person tall? Yeah, not really. Is he not tall? No, not really. So there actually is a sense to what we're doing here. We do have the set of men that are tall and the set of men that are not tall, and one does not totally exclude the other. Whereas for Boolean logic, it does. So we have something I maintain to you makes indeed sense. So that's kind of cool. So therefore, the idea of excluded middle does not apply for fuzzy logic. And I would submit to you that this idea of the law of excluded middle actually makes sense in a common sense sort of way of thinking about things. Because you can have somebody that is not really tall, but somebody that is not tall. There's an ambiguity. There's a fuzzy boundary. That's the reason they call it a fuzzy boundary. So the law of excluded middle does not apply for fuzzy logic. There is the twin brother for the law of excluded middle, and that's called the law of contradiction. So let's talk about that. The law of contradiction says A and its complement is equal to the universal set. This is true for Boolean. So if you have, if you will, a set over here, let's do a little Venn diagram. Here's A. Everything outside is A bar. So if you take the union between A and A bar, you get the universal set. And the idea is for Boolean logic, this should be the universal set. And the membership function for the universal set is 1 everywhere. Everything is included if you have the universal set. Okay. It doesn't work for fuzzy logic. So if you will, the law of contradiction says that the maximum of mu sub A and mu sub A bar is not equal to 0 everywhere. So let's, if you will, take the example that we had in the upper example, and so we're going to have the membership function of men who are tall. By the way, I can't see my screen. If I get off the screen, somebody give me a text, if you will. These are the men that are tall. And these are the men that are not tall. By the way, where is the intersection of the membership function of mu sub A and mu sub A bar? Notice that it always meets at 1/2. So that 1/2 is kind of the area of maximum confusion here. And um, there's a guy named Bart Costco that says this is what maximum entropy is for fuzzy sets. He was trying to interpret entropy in terms of fuzzy sets. I didn't like his conclusion, but it's out there in the literature, so probably I should mention it. So if we take then the maximum, we get this. So this is what we get. This is the set of men that are tall or men that are not tall. And you can see the maximum ambiguity still occurs here at 5'11". And I maintain that if you think about this in terms of the English meaning of men that are tall or men that are not tall, that it actually kind of makes sense. So that's encouraging. So, in conclusion, we see that we have a lot of interesting things going on here. We have the relationship between between Boolean logic and fuzzy logic, and in terms of the commutativity, the associative things, the distributive things, the continuity things, and the meeting of the crisp boundary conditions. Let me talk about the crisp boundary conditions and how indeed they are met. Suppose, for example, we have a membership function for numbers which are greater than 1. So a is equal to x such that x is greater than or equal to 1. Is that okay? So the membership function for that is going to look as follows here. Again, all crisp membership functions, conventional Boolean logic, have values of either 0 or 1. Let's first of all look at numbers greater than 1. Let's look at the complement. Okay, a bar is equal to the set of x such that x is less, or x is, well, let me do it this way. X is not greater than or equal to 1. So that's a bar. Well, what does a bar look like? Well, a bar looks like this, right? Is equal to the values of x such that x is less than or equal to 2. I got my mins and maxes confused. The minimum of mu sub A and mu sub B, and the minimum is looking like this. The only place that the minimum is going to be non-zero is both where the membership function of A and B are exactly the same. So this is the minimum. So indeed, this is the membership function for numbers which are greater than or equal to 1 and the numbers which are x is less than equal to 2. And you can see that, yep, this makes a lot of sense because this isolates all the numbers between 1 and 2 as the intersection of the set. So this indeed meets the boundary conditions of what we would expect for conventional Boolean logic. The Boolean logic works very, very nicely as a special case of the laws that we've put down for fuzzy membership functions. I want to talk next about something which is kind of cool, um, and that is the idea of an alpha cut. We've kind of alluded to alpha cuts before in the case of drunk driving. We all agree that there is a fuzzy membership function for being drunk, correlated with the percent of your blood alcohol, which increases monotonically. The more blood alcohol you have, the more you are drunk. But different states have different thresholds for blood alcohol level and the definition of being drunk. So let's look at a membership function for your blood alcohol. Your blood alcohol and your degree of drunkenness. So this is a fuzzy membership function for, if you will, the degree that you're drunk. And clearly beyond a certain threshold, that's what it is. Now, it does turn out that the states have to come around and they have to say, well, we're going to do a threshold. And as I mentioned previously, probably the threshold in Texas for being a drunk driver is different than the threshold in Massachusetts for being a drunk driver. So what do? You want to make this fuzzy set into a crisp set. So you do an alpha cut. What is an alpha cut? An alpha cut is where you choose a value of alpha and you go across, and everything above that threshold goes to a 1. Everything below the threshold goes to a 0. And if you see, if I choose alpha at different places, I'm going to get different crisp sets. So this is how, if we have a fuzzy membership function and we want to make it into a crisp membership function, one can normally apply an alpha cut. They do this, for example, in terms of being drunk, and there's a number of other things. Going too fast on a highway. Uh, Boy, if you've ever gone to the toll roads in Texas, you can go with a speed limit of 85, which I think is really kind of cool. But why is it 85 there, yet on interstates, which are built just as well, it's 70? It's because they have a different alpha cut. They have a different condition for the speed limit that is indeed safe. Here's what we've done so far with a little highlight going to my iPad is that fuzzy logic fails the law of excluded middle was one of our conclusions. Another one of the conclusions was that fuzzy logic fails the law of contradictions. But I think I made the case that, well, in a linguistic manner, if we look at the semantics of what we're saying by tall men and not tall men, this actually makes sense. It does make sense. So we do not meet these boundary conditions of Boolean logic, the law of contradiction and the law of excluded middle. Now, there are numerous other operations other than min and max for performing fuzzy logic operations. Uh, for example, intersection and union operations. One, for example, is simply multiplying the two functions together. Now, what we've seen before is that the membership function for A and B was equal to the minimum of the membership functions for A and B. Somebody else came along and said, we can multiply these two things too, and we get kind of the same sort of result. We don't have to take the minimum, we can just multiply the two. And then they said, well, we don't really need to take the maximum between the two. We can just add the two membership functions. Well, there's a problem if you add the two membership functions. You can get a membership function greater than 1, and really that doesn't make any sense. So therefore, we take the maximum of mu sub A and mu sub B, and then we see if that's greater than 1. If it's greater than 1, then, well, we just give it a value of 1. So therefore, we add the two membership functions. This is the way to think about it. The union is adding the two membership functions, And then if it exceeds one, we give it a value of one. So that's a possible way of doing things also. I think that next time when we meet, we'll talk about making ands and ors between two dissimilar things. What, for example, if I have, this is just a little tease, what if I have the membership function, we call membership function of a set G, which has to do with liquids that taste good. By the way, it should be important to specify that the opposite of good isn't bad. The opposite of good is not bad. The opposite of good is not good. So if you talk about the set of tall men, the complement of that is not the set of short men, it's the set of not tall men. You always have to put not before what you're talking about. So anyway, here is two different membership functions, and these don't share the same ordinal value. We have the set of things which taste good. I think swamp water doesn't taste good, and maybe radish juice on a scale of uh, 0 to 1 maybe has a 0.5. Probably doesn't taste terrible, but probably tastes better than swamp water. And this is 0.9, which is a really good idea of what grape juice is. And then we're going to revisit the case of cities that were close to Los Angeles. Remember, Los Angeles was a zero point 0, Chicago was a zero point 0.5, New York was a zero point 0.8, and London was a zero point 0.9. What if we wanted to and these two together? Now, it's weird, but we can actually do it. And this becomes kind of an outer product where previously it was kind of an inner product. We're actually going to come up with a matrix. We're going to look at the set of liquids that taste good and the cities that are close to, or cities that are not close to Los Angeles. We're going to do the and between those two groups. And the question is, how do we do this? They do not share the same x-axis, if you will. So we can't take a minimum and maximum because we have different units, if you will. Okay. Thank you, and be of good cheer.